I'm really excited to moderate this panel. Actually, the moderating part's pretty simple. I'm not going to be doing much except giving a basic introduction to everybody here. But this topic is something that is emerging. I don't know, when I started in this biz a dozen years ago in the US doing closed loop systems, well, actually it's more than that, it's about 16 years ago, nobody mentioned inclined boreholes for closed loop geothermal. I've learned a lot since then, and this group here is going to kind of give all of us a bit more of an education about the history and the advancements in closed loop technology. So something else I find funny is at my job, people often say when they introduce me, Dave's the expert at this. He's so accomplished at this, and I kind of just grin, and I know the reality of it. This is the group of experts. You know, there's more, I think, PhDs on the panel here than there are people on the panel right here, both somehow. So, yeah, it's my pleasure to introduce this group discussing specifically the designing of Borefields with angle drilling and some of the history behind it. I'll start by introducing Dr. Goran Hellstrom.
Good afternoon, everybody. It's really fun to be here in New York. I'm from Sweden, where things in ground source has been kind of hot for many years, but it's exceeding that here, and that's really fun to see. I started out as a PhD student in 1977 on studies on ground source heat pumps, and the core of my activities has been simulations and design of everything kind of underground, injection, extraction, and storage. And today I will speak about kind of a introduction, brief history of inclined boreholes. We started quite early with that in Sweden. And so the guys here will follow on and speak about the activities in the States. So let's see here. Oh, this is that one. Okay. So inclined boreholes. So when we talk about angles, we are talking about inclination away from vertical, as depicted in this figure here, and then we also have an orientation, but that is kind of a minor issue in this presentation, I have to say, but not in the design. So the first example is from 1977. As far as I know, there was one borehole drilled for energy purposes in Sweden before this, and this was the second project. And I think it's also the first multiple borehole installation in the world. They started drilling in November 1977, and they completed 42 boreholes. The depth was perhaps not so impressive. It was about 20 feet, a little bit more. 65 feet, and a little bit more. But the purpose of this installation was to store heat. So it's a matter of seasonal storage of solar heat, and the variation of the temperature in the store was supposed to vary about between 77 and 95 Fahrenheit. And it was a combination of high temperatures solar collectors, low temperature solar collectors, and the idea was to use the store temperature directly for heating the house. And here you can see let's see, is there a pointer here also? Or? I don't know. Well, to the left you can see the storage. It's basically 3 zones, A, B, and C. And below that you can see how it was configured. The zone A, the center one, had 18 boreholes to a depth of 75 feet, and the vertical ones. And in B, you had 12 boreholes to 66 feet with an inclination of 13 degrees. And then C, it was the inclination was increased to 20 degrees. And the purpose of this inclination was to create a suitable volume of rock, a certain capacity for the intended amount of energy to be stored, and also to reach the temperatures. if the boreholes are spaced too far away, you will not have heat transfer capacity to raise it to that working temperature in the time that you have to do that during the summer. So here it's a matter of having the right spacing and the right volume. The ground surface area was a bit constrained, otherwise they could have used vertical boreholes, but so they started out small, and the size you see in the middle, that's the configuration of the boreholes. It's about 10 meters across, and in the bottom it's about 25 meters across. That gives you the right volume, and they also want to have a compact volume. They don't want to drill, instead of 42 boreholes, 4 boreholes to 850 feet or something like that, to have the equivalent number of borehole meters, because that will give you an elongated shape and excessive heat losses. So, and the second one, which is kind of interesting, the objective of this system here is to extract heat for single-family houses outside Stockholm. And you can see in the left picture there a picture of the system with the boreholes, and also recharge from low-temperature solar collectors that were put on the top of the garage. And the configuration is like you see in the middle. It's kind of a star-shaped configuration, and the inclination of all boreholes is 15 degrees in order to reach out to a large volume and minimize the influence between the boreholes, and to access then, to expose the boreholes to the surrounding and get rid of the kind of cold that's generated during extraction. This is a standardized market offering, and they had 2 depths. One was 500 feet and the other one was 600 feet. So there was a standard heat pump, a standard configuration, and they sold this for a couple of years until there was this kind of reverse energy oil crisis around 1986, when the oil prices dropped 80% and oil became so cheap, so alternatives had no possibilities. In 1986, there was another project in Stockholm where they have, you can see to the left, there are 2 kind of buildings enclosing an inner court with a glazed roof. And during the summer, it gets very warm if they don't remove the heat, and they remove the heat and put it into the borehole. So there was a storage. This was a kind of storage. It was not an elevated temperature, but due to the heat balance, it's fairly balanced system, they could put the boreholes fairly close. And you can see to the right what it looked like. And to the left here in the upper part, you can see the ground surface arrangement where they started drilling. So it's a grid of 5 times 5 boreholes with a spacing of 6.5 feet. And the footprint is 26 by 26 feet. At the bottom, you have a wider spacing in order to access a larger volume. And I could also mention here that this is a way also to design systems with inclined boreholes, that you, instead of starting from the ground, so to speak, with a layout, you can make a regular grid in the bottom of your expected target depth. And then if you have an irregular placing of the boreholes due to peculiarities at the ground surface, you can connect them to the bottom grid. So that's a way of proceeding. The maximum inclination here was around 8 degrees. Here is another one from 2008. It's fairly large. At the time when it was built, it was the largest system in Sweden. The objective here is to extract heat. There's no recharge. So in order to achieve that, you want to spread the boreholes as much as possible, but there is a constricted area. And the boreholes are drilled from the inner courts of each group of houses. The spacing between the boreholes is about 20 feet. And they are 750 feet deep, and the inclination for most of the boreholes are 15 degrees. but you can see in some places they are close to each other, and then at some points it's constrained to 5 degrees. In total, 156 boreholes. Yeah, that's the way it looked from the side. Here's another example. This is a telephone switching station or a data server that's rejecting heat to the ground. There's a lot of installations like this in Sweden. So the main telephone provider, service provider in Sweden, they are using free cooling to the ground. So they are rejecting heat without the use of a cooling machine. And in this case, they have free cooling of the data server, about 1.2 megawatt continuously throughout the whole year. And actually, if they are not connecting it the way they have been done here, it's about 40% of the energy is rejected to the ground during the summer, and in the winter when they have cold air temperatures, they reject that to the outside air in order to not overcharge the ground. In the summer, the air is too hot for free cooling. In this case, there is a campus nearby, so they charge the boreholes, and the charge energy is extracted by a heat pump for the heating of the campus during the winter. And it's the same. The heat goes directly to the heat pump in the campus. 82 boreholes, and they are placed in a trench, and the spacing between the boreholes is 5 feet, so it's 40 boreholes in one row, and there is 5 feet also between the rows. So it's very compact. It's 200 feet long and 1.5 or 5 feet wide. And the boreholes are 1,000 feet deep. In this case, they also measured all the boreholes, and it turned out that it looked pretty much as they had designed, with an average deviation, a target depth of 28 feet, about 2.8%. I should also mention that in Stockholm, center of Stockholm, inclined boreholes are a fully approved concept. So the designs or the intended drilling is delivered to the environmental office of Stockholm City, and they will approve it. You can see here inside red, that's the center of Stockholm. There are lots of installations, and they are fairly large. It's apartments and office buildings, whereas to the left you can see some of the suburbs of Sweden where you have single family houses, and in that area almost all houses have a ground source heat pump. This is a case or a part of the inner city of Stockholm, and to the left in red you can see at the bottom the street, you can see the buildings in gray, and then you can see the kind of inner court behind the building. And for the red ones, encircled ones, the drillings are done on the inner court, and many of the boreholes are then inclined to access a large volume. In blue, you have another case where it's drilled on the pavement. Yeah, and about 2/3 of all boreholes are inclined. So it's a concept that's been used for a long time. Yes, here's another case. I just wanted to show here. Let's see if I can. If you look to the right, you can see a vertical view of the temperature field, and to the far right you see a horizontal cross section, and this is the winter peak ground temperatures, and in this case the system is completely balanced. And if you have a balanced system, there is a certain reach of the wave, the heat wave that goes out from the borehole and back again. So going beyond this reach doesn't really change much when it comes to thermal influence. So there's a difference if you have a heat extraction or heat rejection system only, because then it will spread across the whole system. So well, there it started. So this is the quick 5-year animation of the system, and you can see how the heat goes back and forth in this fully balanced system. Just to mention, if you look on the dates here, the names are not so important, but if you look on the dates, you can see that there are some early publications or studies being made, and then it kind of picks up. So the interest for inclined boreholes have picked up in the last years. And finally, there were some early design tools made. In 1987, Eskilsson presented, at Lund University, presented design tools, but they covered 2 to 9 boreholes in predefined configurations, some of which you can see here as an example. And to summarize, the advantages of inclined boreholes is to reduce the footprint of the borehole configuration, and that also increases the flexibility of the borehole locations. You can make them kind of regular, deeper down, but you can put them in better positions at the top. And it's also, you want to increase the borehole spacing to reduce thermal influence and increase the thermally active ground volume. And in some cases, when it's a storage, you want to create a suitable shape and form of this storage volume. And now for more details on simulation and design, I ask Jeff to continue. Thank you.
Thank you, Goran. Okay, so I'm going to speak a little bit about using GLHE Pro or GLE Pro to design angle borehole ground heat exchangers. So GLE Pro, GLHE Pro is a simulation-based ground heat exchanger design tool. It can do vertical boreholes, horizontal ground heat exchangers, angled boreholes. Could even do like curved boreholes that you might get if you were using a horizontal drilling rig and you went down 15 feet and then came out somewhere and pulled the loop back through as line segments. It models heat pumps, and the first version was released 30 years ago. We're on version 5.0 right now. So the user inputs the ground properties and information about how you finish the boreholes, heat pump characteristics, and the heat pump loads, and you can also do loads directly on the ground. And then it adjusts the size so that you hit either the maximum design temperature or minimum design temperature. So the basis of the simulations is called the G function, and this is a thermal response function that gives for a fixed pulse. It would give the dimensionless temperature rise versus dimensionless time. And all the complicated, or maybe just almost all of the complicated mathematics are in getting this G function. So just as an example, with straight boreholes, here's 2 fields, a 6x5 field and a 30 borehole field with elongated open rectangle. And you can see that the orange curve for the 30 boreholes in this more compact configuration, it rises faster because you get more heat buildup if you have an imbalanced system, or heat drawdown, depending on how it's imbalanced. Right, and then since for about the last 8 years, we've had this capability to calculate these G functions for angle borehole systems using what we call the free placement finite line source algorithm. And I was talking to somebody earlier. I said, well, we have a modest capability for doing this. We can do it. It's not very automated, so the user has to specify the position of the top of the borehole, the direction that the inclination is, and what the inclination for vertical is at. You can import from Excel, which is, whenever I do it, it's always how I do it, because I think it's really tedious to type in this information. So it's much easier to import from Excel. So I just started an example, and it'll show you some sort of simplified drawings of the field: front view, top view, side view. And this is the form you would import the boreholes in. So just did a short example. It's a medium office building in Atlanta. It's cooling dominated. I made two designs, a conventional design, a 4x8 rectangle with vertical boreholes, 20-foot spacing, and I'm calling this a circle installation. So you have a drill pad, and I think I have a 13-foot diameter circle that I assumed you started from, and I alternated the angles between 9 degrees from vertical and 18 degrees from vertical back and forth. And then I did 9 boreholes, so I realized I ended up with 2 9-degree boreholes next to each other, but at that point it was too late to go back and change it. So that's what we've got. So I took a guess at 700-foot length. This is what in terms of the horizontal deviation, one is at the bottom is 110 feet from the center, the other is 216 feet. And I used Excel to put in this information. I calculated the XY positions on this circle using trigonometry and put in the 700-foot length. I used the import file, the little circle button there to import that information. And I got the results, which maybe look a little strange, no doubt. Because the FPFLS can also do different depth boreholes and so on, we report this sort of correction to what you put in earlier. So instead of being 700 feet, they're just 654 feet, 9 boreholes. And we sized to a maximum temperature of 90 in 30 years. And then all the inputs here are shown on the right, or most of them. So for the 4x8 rectangle, similar, we ended up with, if we use 32 boreholes, they're 582 feet deep. So for this example, we used 2 of these. Yeah, I'm good. Used 2 of these circular drill pads. So assumed we had two places on the property. We put in these the circle with the boreholes, under 12,000 feet of drilling. So if you compare to the comparison's arbitrary, a 4x8 rectangle, 20 feet, but we'd save 37% in drilling by using angled boreholes, and we'd have, of course, a lot less surface disruption. If we said, yes, true, but that's because you have spacing so close, it's true. So if we expanded the 4x8 field to have 30-foot spacing, then by comparison, we'd have a 30% savings. So we get the advantage of taking advantage of more ground volume, basically, and since we're angling the boreholes, we can have less surface disruption. So that's GLHE Pro for angled boreholes in a nutshell. Thank you very much.
Good afternoon. Stan, I'm gonna keep moving here. All right, so I decided to be cute and put a angled title on my screen. I'm Stan Reitsma, CEO of GeoSource, and we design and construct a lot of geothermal systems. And I'm going to talk a little bit more, very similar to some of this, obviously, earlier conversations. So you'll see some repetition. I'll try to go through that quickly. So I'll talk a little bit why angle holes. I think, Goran, you obviously hit that on the head about why. Space constraints, so we can get a lot more boreholes in a very small location and spread out under an awful lot of ground. And the reason that we really want to do that is often in cases where you have obstructions on surface that you just can't get to. So existing buildings, utilities, trees, all that kind of stuff. The other one we're really starting to see angle holes used a lot on is in the case of construction where you already are, you can, in the picture to your right shows a drill rig drilling at a police station that's being built. We were able to drill these holes still because we were doing angle holes out under the out under that future building being built, rather than trying to drill under that building or in parking lots beside it, which was an active police station still in service. So we didn't want to get mixed up with those guys. So we drilled off to the side, and this is on one side is Eglinton, which is a major city street running there with all sorts of stuff, and then the building off to the right. And that's the kind of application that we're seeing for angle holes quite often. Minimize tie-in interferences, so really starting to get away from other infrastructure that's already there or future infrastructure. Also, obviously, the third one is, having a job where you're working on and there's some obstructions, there's future, stuff coming in there that's just going to be in your way while you're constructing. And, talking about one Java, that, angle holes there may have been a great spot because the construction activity there, the drilling and the other construction activity really conflicted with each other during that piece. So angle holes can play a role there. And then, and then the last one, I really want to talk about this. This is one that's often missed. So we're talking about, you got a football field outside your university or school that you're like, okay, I'm going to put a field out there. I got lots of room. And then 10 years later, the number of times that we've had these conversations going, oh, I wish we didn't have that bore field under that football field because we got a new building going in there. And so we're like, look, just put angled holes in and put them next to the existing building or the building you're building, and save all that stuff for future use and leave it alone. And that's sort of one of the drivers for angled holes for sure. This is just an example. This is our rendering of what we could have done on a job that we went and looked at. This is Yale, and this is the idea that basically a pyramid, which you're going to talk about, pyramid drilling, going out. Some of the things we're doing in design, so we're talking about design here. Some of the things that you really need to pay attention to when you're designing, is it constructible, right? So can we drill the holes without hitting each other? Can we get them in? Is the mass going to touch up against the building when it's on lean? Those kind of stuff, just be aware of in the design. Of course, tie-in, where you're going to put the tie-in. Can we get these pipes all together? They're really close to the surface. Can we deal with that? One here that's one thing that we have to really pay attention to is borehole collisions, especially near surface. So, and communication between boreholes, because we're drilling holes awfully close together. So when you're constructing, these holes might be as close together as 18 inches together at surface. If you're not taking steps to prevent communication between boreholes, you end up with way more issues than verticals, which are now 20 feet apart, right? So there's just some of that stuff needs to be looked at. And then, of course, optimization, which I won't spend time on. I know that Dmitry is going to definitely talk about that, I suspect. And look, there's a lot of stuff, and some of this is repetitive. So I'm some of the things with angle holes, obviously looking at the volume of rock that you're accessing needs to be there. The behavior is not necessarily the same as verticals, so there is some communication of heat between holes at near surface because they're closer together, but then they get spreading at depth, so there's some of that stuff. Trajectory is a big one. Where are these holes going? And we know that vertical holes are different than angled holes in terms of drilling. So there's some aspects to that and how you deal with that. And then a big thing is how are you positioning your holes? So vertical holes are very easy to position. Well, you put a pin in, you drill vertical. Angle holes, you need to get your direction and your angle of the drilling all accurately placed to get those holes in. So that's so some of the things that we got to be careful of is making sure these holes aren't actually paralleling each other too closely, because we can't get direction as accurate as we may like to, right? So it's just a reality of positioning machines. Okay, so I know a lot of words on this screen, but I just want to show you angle holes and vertical holes from a design perspective. They're largely the same thing. There are some considerations, but from a design perspective, they're largely the same thing. We treat them the same. And if we looked at, I'm just introducing ground loop design. It's a software that we often use, and I know it's fairly common in the industry. There really is only one step difference in a vertical design versus angled. and it's this input angled borehole arrangement details. And the latest version of GLD has this in there, and it's a lot like GLPro. I can see you're basically putting in vertical arrangements, or you're putting in angled hole arrangements, which is an option that you can just select. And it's something like this, and this is, again, looks awfully similar to GLPro, and you could pull this information in from a spreadsheet. But here you got basically your X and Y position of the borehole, your angle and your direction and your angle off vertical, and depth. Okay, so then this is basically the things you add in, and once you have this, it does all the work in terms of using G functions and so on to calculate what the behavior of that field would be given a given load, building load, like you would have with the vertical. And I'm going to go through these. Just an example for a retrofit and new construction in City of Toronto with, it's 240 Markland and Etobicoke, where the site restrictions really forced us into an angled borehole solution. And this is essentially what we designed. And what you see there is a bunch of verticals. So you can do a mix of verticals and angled holes. The verticals are the single dots. The angled holes, of course, are the lines with top location and bottom location and the direction of that borehole. And then to your right is the output from GLD on a 30-year simulation of the building loads interacting with that bore field. And again, if you're familiar with GLD or any of the other software, you'll look at this and go, okay, that's all very familiar. So what I want to point out there for engineering out there that's looking at this, if you're familiar with vertical hole design, you should be able to become somewhat familiar with angles. And there are obviously nuance to that. And then continuing that, this is that design. Now you can see that bore field has been drilled, tied in, so the middle picture is tie-in, and then that bore field laid out on the actual site in terms of what it would look like. This is that building now. There was an infill building going in. You can see that new building being constructed, and it's basically top now and working on the interior. And the existing building has been reclad, and it's all operational and been working already for a couple of years. And then I think I better end there. There's just this is just another great example of an angle hole job that was done, and the main reason for this one was interference with existing utilities. There was so much infrastructure in front of this federal laboratory building that to do verticals would have been almost impossible to do. So this is a angled hole job in front of that building, and that is not a rendering. That actually was what that building looks like. It looks it's pretty cool looking building. Anyways, thank you.
Good afternoon, everyone. Oh, I got you. Thank you. This one. Thanks a lot. It's like extra security step. My name is Dmitry Kuravskiy. I'm from Celsius Energy. There's a lot has been said already by the extremely smart people with PhDs. I'm only a master, so I will go a bit more simple on what we will review here. So we will talk about Celsius approach. We're basically using inclined drilling, but we're using inclined drilling, as was mentioned, as one of probably best applications when we collocate them on the surface. And it's bring multiple benefits to the customer and to basically to everyone. And the key benefits was already discussed. I'll just put the numbers, correct, to just to understand in quantity what does it mean. So when we talk about surface impact reduction, we talk about 95% reduction in surface impact. So we're basically saving 95% of the surface area, which can be in future used for the future construction and basically saving real estate. When we talk about something we didn't mention, but it's significant as well, it's about civil cost and basically piping cost. So all this, especially in New England area, in the States, is extremely costly. So, and we see savings somewhere between 60 to 70% on the total cost. Besides this, if we just compare these bores to each other, we see somewhere between 10 to 20% increase in efficiency when we're using deviated bores because of access to the bigger thermal mass. And what is cool about this is that we can see actually higher percentage of benefits when we have unbalanced loads. So which really critical when we talk about new design buildings with a high efficiency. So in my presentation, I decided just to take example of one of the projects and how we will basically approach this project from the design point of view. So any project we have on the table, first of all, we're just deciding can we drill it or not. So the first step on any feasibility study and any design study, we need to understand the geology. So we do the drillability study. The first step of drillability study, we're trying to understand the geology, trying to evaluate the drilling hazards, complications, water production, bedrock depth, and approximate thermoconductivity based on the geological rocks you can find underneath. After we've done this and we see that the area is feasible for the drilling, we go to the next step. We basically define the property boundaries. We have a special proprietary software. We basically can punch any address in basically worldwide, and then we can see the property boundaries of the property which you're interested. So we're basically mapping up the property and we're loading in our software. When we load in our software, we basically move to the next step. So we load up in software. This is kind of the property boundaries of one of the higher education place. What on the next step we define, we're basically putting all the buildings which we have on this property, correct? And what's cool about this step that besides the building, we're putting foundation as well. So we're basically putting at least 30 to 50 feet foundation to make sure we account it when we plan for the inclined bore. On the next step, in this case, it was actually quite interesting study because this facility already had a field of the geothermal bores in the middle. This facility has roughly 50 bores. Because we didn't have information about the direction and inclination of these bores, there was no any survey done. We basically apply ellipse of uncertainty to where we guess these bores can be. So we apply worst case scenario. We assume 40% deviation at least. So we apply 250 feet radius around this field to make sure we account for the possible position of the bore field. And then we basically space it out up to 500-foot depth and create a 3D model basically with property boundaries, buildings, and the future existing geofield. Knowing all this, we position our pyramids, platforms, or basically collocating points where we will locate our bores, correct? So we basically locate at least 5 different locations, which basically you position them based on the existing constraints of the facility. We account for the property boundaries. We account for the step out and feed. How do you call it? Step outs from the utility lines, from the electrical lines, because there is quite a lot of regulations, and you must respect the distance from every utility which existing on this facility. And quite often, this step outs is actually causing multiple months and probably even years of delay to be able to get exemption from them. So after we set up the surface locations, we basically run the software. The software is smart enough to basically assess the thermal need of the building. We basically load up the thermal needs of the building. It can be 8760, it can be monthly data, it can be yearly data. We load up the demand, we load up the geology, we load up thermoconductivity, parameters of the bores, like what depth we want, what maximum inclination, what space out between the bores, and then select the completion type. I don't know, a single loop, a double loop, is it cut-centric, whatever is more applicable in this project, and then we run it out. So it takes normally somewhere between, I don't know, 5 to 10 minutes. This is a project quite small, it's around 100 bores. So it takes around 10 minutes to run the whole project. And then we're getting the whole basically thermodynamic model with G function, and we can basically see the prediction of the T-min, T-max for the next 25 years. I didn't go in details because we're more concentrating here on the design and drilling. So I didn't go in details of the output and output and overall. As a fun element, I basically done exercise and I basically maxed out the software by reducing the spacing between the bores. So we basically maxed out this case up to 500 bores basically. So it's 500 bores. And the only limiting factor in this case is basically the space requirement, correct? So we just could not physically fit more bores at this territory. So when we basically done modeling and we define how many bores we need based on our thermal loads, the next step is basically to understand what execution design will look like. Because I do agree there is small difference between vertical and inclined, but there is a quite critical steps you need to account when you execute the inclined bores. One of them is basically the torque and drag calculation, because when you go under the angle, the inclination and gravity works against you, so you need to account for this, and it's need to be accounted in every single step. You accounted for the drilling, tripping, for the completion, basically loops running, and you even accounted for the grouting operation to make sure the pressures will be in line with your expected models. On the next step, you design bottom hole assembly based on the inclination angles, you basically, and azimuths requirements you have for your project. And one of the probably most important, and Stan actually touched really good point about, for example, communication between the bores, because the bores are located really close. So the communication between the bores, the well bore stability, the collision. So all this basically risks need to be taken into account, and they play quite critical role and can get way more damaging factor compared to the vertical drilling. So we basically run risk assessment based on the geology assessment, based on the bedrock depth, based on the technology we need to apply. And then we basically move to the cost analysis, which I didn't include here. And then we're ready basically for the proposal to the customer. So that's it on my side. Thank you a lot.
And the risk. Yeah, high risk.
Yeah, that was great, right? So I think we had about 3/4 house and almost full house now, so there may have been a couple things missed by some people. And there are probably lots of questions, so we'll just have Max go. We're going to pick side-to-side rooms, so make sure he continues to get more steps in.
Is there a maximum angle where you can kind of assure you're not going to collapse? I've heard that certain angle boring you can have collapse in the borehole. And is there an angle you stay safe with, or is just that not an issue?
I'll take the microphone and turn the microphone on.
In our case, basically, there is two limitations for the angle. One is basically the collocation itself, the way we deliver. We have a limit somewhere around 22 to 24 degrees. But if you look from the holistic point of view, the angle you will stay away from, it's probably somewhere around 30 degrees, because at 30 degrees, the mechanics of the wellbore cleaning and the gravity distribution is changing. So and you start to get in way more complex way more complex challenges, and to be able to address them, I mean, you need to spend way more. So if I would plan, I would probably stay below 25 degrees to be on safe side.
Is there a limitation? Oh, I'm sorry. Did you want to answer that too?
Yeah, I would like to add something. I talked with one of the more experienced drillers in Stockholm, where we were drilling crystalline rock. And he said he was very comfortable with drilling up to 20 degrees angle. And after that, there was some concern about working conditions for the driller, because it was kind of heavy to direct the rods into the connecting the rods at an angle. In Sweden, there is an impression that you don't really have to pay extra, or that for angles up to 15-20 degrees. We have had installations in tunnels where they have drilled up to 40 degrees without problems, I would say. So, but 20 degrees is perceived as a limit, kind of, I would say.
Is there a limit with the bore diameter versus the U-tube pipe size that you can use, or optimal size? 3/4 inch, 1 inch, 1.25 inch loops. Is there a recommendation or limitation with the drilling equipment that's available?
Yeah, so tying to the earlier question, I think if you stay below, say, 20, 25 degrees off vertical, there's not a lot of difference between a vertical and a angled borehole. So that all your pipe dimensions, your borehole dimensions, and all the way you grout the hole and insert the loop, from our experience, all remains largely the same, whether it's vertical or close to vertical. I think once you get up into above 30 degrees, I suspect, we haven't gone that high ourselves, so I wouldn't know, but I would say that you're starting to get into some challenges with some of those things that you're asking.
And I think one more important item here when you're discussing the diameter, it's more about economics. So when just need to consider, I don't know if it's open information or not, but I done some studies on the diameter and relation to the drilling performance. So just jumping from, for example, 5.5 inch to 6.5 inch, you're actually increasing effectively the amount of cuttings you remove, water you produce, and the amount of rock you need to break by almost 70 to 80%. So if you basically monitor the performance reports, you can see that at 5.5 inch, you probably can reach up to 200, 250 feet an hour as max in the granite, for example. At, for example, 6.5 inch, you're looking at max probably 140, 150. So there is a substantial reduction in the drilling performance. And on another side, you have a substantial increase in the wastewater management and the cuttings management. So every time we go to the high size, we need to take this in account and run economic analysis. Is it makes sense in this case to go with bigger bores? Is it because it's limited and we basically trying to go deeper? Or for example, when you go inclined, you already get an expensive rig, you already get expensive setup for the drilling assembly, everything is ready. So in this case, you probably would prefer to go as deep as possible to make sure you make it one shot and then economic work out better. At least this is how we approach this.
Hello, thank you for the educational session. I feel like we should all be up for some CEUs probably after that one. But I have a question about the borehole installations in Stockholm, I think you said in Sweden. So in an area like Stockholm, where you have so many residential houses that already have their individual boreholes and geothermal heating for their individual residences, is there a chance to transition to a networked system in a neighborhood that already has boreholes using the existing individual residence boreholes? And would that make sense, or would that be a practical thing to do?
Yeah, that could make sense. If you're talking about single-family houses, I don't think that's so important. But when you get to larger buildings, certainly if there's a mix between apartments, for instance, and offices or industry, if there are sources of heat, because in Sweden it's usually heating dominated. So we have to recharge, and then if we have to recharge to pay for it, that's one thing. If we have to cool buildings, there's a benefit in doing so. So if we can connect buildings with different energy loads to get a more balanced load for a certain area, that's good, and that has also been done, and was done. Like the first case to demonstrate that was in around 1990, when they had one building with just heating for apartments, and then they had an office with heating and cooling. The office building could not do free cooling by its own, but when they connected to the apartments, they had possibilities to do free cooling, and then the free cooling would recharge the residential, the apartment part. So that was beneficial for them, and it was beneficial for the office because they could do free cooling and reduce their cooling costs.
I've been at the Sun Court in Stockholm. Back in '86, we had a group from North America went to visit the project, which is I remember was a courtyard, and the drilling was underneath the courtyard. and the holes were accessible because it was water, not grout. And it's because of granite or because of rock. Now, how does that work if you have a not granite or rock and you have soft soil and overburden and you're going that depth? How does that look with the collapse of the boreholes?
I mean, we're using permanent casing through the soil, so that's not a problem. And if you're wondering about the thermal performance of water-filled boreholes contra grouted boreholes, I would say that for heating, when the temperature in the water is low, there is not so much natural convection between the pipes and the borehole wall. So the effective conductivity of the water is slightly less than modern thermal grouts. But when you are cooling and the temperature is higher, it's about the same performance. But the cost of grouting, at least in Sweden, is so high, so it's more beneficial to drill a little bit more to counteract the slightly lower performance of the filling material in water-filled boreholes. So it's not done, it's not grouted if it's not required. It may be required close to primary water protection areas, not otherwise.
And just to add, there is probably another two methods, like at least we utilize them in Europe as well. One method is basically double head drilling. So when you basically drill with casing and inner strings at the same time. So basically you casing as you drill. And then you basically run your loops, you grout, and then you retrieve the casing, because casing quite costly. So, and with the steel prices going up, it's can add up pretty quickly. Especially if, for example, your bedrock, I don't know, you talk about depths, 100 plus foot, it can be substantial cost on the project. Another approach is basically coming from more oil and gas approach, is basically to running the proper mud systems when you set up properly the mud using the polymers, which will basically hold up the well bore and add up the stability to the well bore. So, but you need to be very cautious about mud properties and the mud weight, correct? And this helps to hold basically the bore intact at the high angles.
Just one question on cost optimization. Have you seen any other research studies or just in your experience patterns that lead to well-behaved optimization functions, so you can kind of come up with some rules of thumb for dollars per kilowatt hour or dollars per kilowatt in terms of trying to minimize the cost of these installations? Or is everything just different?
I think the answer is that the angle holes are not a lot different costs than verticals up until a certain angle. I think there's some, once you get past a certain number, it gets tougher. But so if we have that for verticals, it should apply to angles. I don't know if we have it for verticals, but I don't see a lot of difference between the application of the technology.
I'll just mention, I was working on optimizing some borehole designs, and since between June and October this year, I got quotes on drilling per foot that varied from $10 a foot in Oklahoma to over $100 a foot in New York. So trying to come up with a rule of thumb in that environment is difficult, to say the least.
And I would add a bit on the difference between cost for the angle drilling and vertical drilling. It all depends on your requirements in terms of quality control. If you basically ask to deliver the deviated bore and you're not asked to basically to survey them, this is one item. If you, for example, have a contractual obligation to prove that you're in 5% tolerance, then you need to apply the technology and means and methods, which quite costly, because most of the stuff is actually coming from oil and gas, and the prices here is much higher. Just to give you example, like in framing game, to be able to hold the assembly at inclined angle, we need to maintain the tolerance of 0.01 inch at the assembly. As long as the moment it's tolerant, we basically get some beads from the local manufacturers, and we ordered 6.5 inch beads. The beads come out. Some of them was 6.4, some of them was 6.6. So the one which was 6.6 was dropping some around 10 degree every 500 foot. The one which was 6.4 was building 10 degree 500 foot. So this is from where the cost is coming.
You talked about interference to the boreholes up top. Is that purely just fitting in the drill rig, worrying about interference, or worrying about thermal interference once it's installed? And are there certain minimums you just don't want to violate in terms of spacing?
Okay, I probably can start. Stan can add. So, I mean, there is definitely thermal interference, but it's taken into account at design stage because the bores is closer at surface. We definitely lose a bit at the beginning, but then because the bores at the bottom spaced out, I don't know, 4 or 5 times more than traditional, you're gaining, and this is basically offset. As a result, this bore's more efficient. But what Stan mentioned initially, and I was basically picking back, it's more on the soft bedrock. Before you, for example, in Northeast, before you reach the hard rock, which basically where you can seal your casing, because, for example, you're using the high pressure air or you're using the high pressure fluid to circulate, this fluid under the pressure break through to the nearby wells and basically pushing your grout out. So it's extremely critical when you develop the inclined bores to create a proper seal at the bedrock to be able to maintain the integrity inside the well bore. And this is sometimes it's quite challenging and adding again to the cost aspect as well.
Yeah, we didn't define communication. I think that you know, the difference between interference, thermal interference, and communication. That's what the difference is. That's all right. Everyone did it.
Right. They're both some level of communication, but the circulation interference is definitely something we got to. Our experience with that is, let's say you're running casing and you're pulling casing, which is what we normally would do. We would leave an awful lot of the casing in until we're a certain distance away from the next hole being drilled before you go back and pull casing on a hole that has been drilled, you know, a week ago or so. So there's some, you know, how you would actually progress through your drilling is also important, particularly when you start getting angle holes. Because we are at distances as close as 18 inches apart at surface, center to center, which means the holes themselves are less than 12 inches apart in the top, you know, 10, 20 feet, right? So there's it's definitely unique and different, and you know, should be paying attention to that, which in our case just means generally we need to leave an awful lot of casing on the job site and prepare for drilling 20 or 30 holes before we start pulling casing back, which might mean we need, you know, 2,000 or 3,000 feet of casing on site before in order for us to progress through far enough before we can come back and pull casing to run onto the next hole. So but yeah, all these kind of aspects are different from from vertical to angle.
Take our
May I just add that in Scandinavia, where we use groundwater field boreholes, we use permanent casing. So in the first bit there is a casing always there. So we have had little problem of that sort, and we have also had installations with just 18 inches between the boreholes at the top.
Take our last question. Mr.
I guess
Carino.
I got 2 questions. When you design, do you figure a percentage of deviation, or do you run deviation logs to see where the bottom of these boreholes are in your design, or you're just drilling, putting a loop in, and hoping for the best? That's my question.
I mean, you design, so the way, like at Celsius we approach it from both sides, correct? So you design with certain angles, like in our pyramid solution, we basically have a different inclinations. You look from 3 different sets. You have actually at least 1 or 2 vertical bores, then you have a 7, 14 or 20 degrees bores. So you deliver, after you deliver, actually as you execute, you basically measure the inclination and azimuth, so you understand the response of the assembly and the given rock, and then you basically tune your assembly based on your feedback, based on the tendencies of inclination and azimuth you see, and then you keep going. And as a last step, when you actually deliver everything, you survey everything, we take these bores and we load them back in the model, and we basically recalibrate the model, and we see the actual result we see in terms of thermal performance.
Yeah, that's almost perfect timing with very little deviation. So, yeah, thanks everybody for attending the panel.